So I'm going to be talking about one of my PhD projects today. Overall, my PhD is looking at how large-scale climatic events have shaped the evolutionary history of squamates, squamates being lizards, snakes, and amphibians. Squamates are quite a cool group, in my opinion. They have over 9,400 extant species and have managed to do some pretty cool things. You have several instances of gliding. You have the ability to run on water. They've both managed to adapt to hunting in fresh and salt water. You have some of the smallest vertebrates that we know of. And you also have the evolution of a venom system. And this diversity is really interesting, particularly because it means we have a lot of molecular data that we can look at. And in fact, for squamates, over 4,000 species have at least one gene sampled. They also have quite a long history. Their closest relative, the tuatara, is now just living in New Zealand, but the two clades split about 250 million years ago. And some particularly interesting groups are the mosasaurs and the polyglyphanodonts, both which were quite successful in the Cretaceous, and then died out at the KPG mass extinction. Following that, you also have some rather interesting forms like Megalania, which is a giant version of the Komodo dragon, lived in Australia, as well as some giant snakes like Gigantophis and Titanoboa. So not really things you want to meet, and luckily they're not around anymore. But as interesting as the fossil record is, it is a bit lacking in quality. For example, for snakes, what you tend to find is vertebrae, and whilst the vertebrae are very good at telling you that snakes are present and may give you a rough idea of what type of snake is present, the characters are very homoplastic, and there's generally a lot of problems with the morphological data. And this is why I'm using a molecular approach to looking at events in the evolutionary history of squamates. So to do this, I'm using a subsampled matrix. I'm using about 159 taxa coded for up to 52 genes. And these were chosen to represent all the major groups and also all the more basal divergences in these groups. And I'm looking at this using Bayesian methods in phylobase. So I built my own tree. And then I'm using molecular clock methods to estimate divergence times and see when in the history of squamates have they had times of particularly high diversification. So there are two main things I'm testing to see how robust the pattern I'm finding is. And so in phylobase, I'm looking at different relaxed clock models, both autocorrelated and uncorrelated. So I'm allowing the clock to be relaxed rather than strict, so there's not a global clock for all of the taxa, which makes sense because some of them are really distantly related, especially the outgroup taxa. And within that, you have different methods of how local clocks might be related to each other. And I have a calibration set of 46 calibration points. Both the calibrations and the outgroup taxa we find to be really important when doing preliminary analyses, because it's the main difference between my results in previous attempts at doing this, and it also recovers very different times. Then, because the calibrations are so important, I'm also looking at the priors on the calibrations, and I'm using NCMC tree and PAML to do this. And here you can see an example of, these are all for node 6, so the split between squamates and the tuatara, and they basically exemplify how much trust we have in the fossil record. So if we think, actually we think that the true age of this node is somewhere between the minimum and the maximum, but we're not too sure where. We might use a normal distribution, or if we think probably our fossil is quite close to when these two clades diverged, then we might use a prior distribution which puts much more weight closer to the minima. So here you can see a quick overview of my calibration points. What was quite important for us is to have them nicely spread out. But what you might also notice is there's a lot of minimum-only calibrations, and that's because maximum calibrations are really difficult to get. You usually have to do them based on absence of evidence rather than evidence of absence, so they can be a bit contentious. But for PAML, you need both minima and maxima, so I just approximated very loose maxima. So the base tree that I'm going to use to show the results on is this. So this is based on some of my phylo-based results with the CIR process, which is an autocorrelated relaxed clock model, and these bars represent the 95% confidence intervals, and the lines are the mean estimate for where we think these divergences happened. So in comparing the different relaxed molecular clock methods, you can see that the different ones, even the uncorrelated one, which is the gamma, CIR and log normal are both autocorrelated. So they're all extremely close together, they overlap a lot, and the confidence intervals are quite narrow. This is probably because I have a lot of calibrations, but it does mean that we have some confidence that all of these events are happening within such a short period of time, and that's really the pattern that I'm looking at in this project. Previous results have found this group of divergences to take the entire length of the Jurassic. So when I started doing these analyses and suddenly found them all to be bunched up, we were quite surprised. But we keep getting this result, even when we through the different models at it. So we think that there might actually be some interesting pattern in what's happening. So some of the calibrations are on these nodes, so I wanted to test what would happen if I remove those. And as you can see, it's still pretty consistent. And then I started more recently doing some preliminary work in PAML. So these results, as you can see, are suddenly a lot less consistent with what I was previously finding. And essentially, both the skew normal distribution and the uniform distribution put a lot of the distribution sort of density much further away from the minimum. So my current idea is that probably this is being affected by my very loose maximum calibrations that I've set. The internal nodes should truncate some of this effect, but I need to look into this further. Now, when I looked at the skew-T distribution, which puts the weight much closer to the minimum, you can actually see that in the pale green, that the confidence intervals are much closer to what I was previously finding again. In fact, they're estimating some of these nodes to be even younger than we previously thought. And what I also tried was randomly assigning the distributions. So I had my nodes, used Excel to randomly tell me which distribution to take for each node. And this, you can see the confidence intervals are much narrower and against much more congruent with the previous results I was getting. And this is probably because the internal nodes are sort of keeping each other in check. So the reason I call my talk a long fuse, I've cropped out my other outgroup taxa, but you can see that it's an incredibly long time between the divergence with the Chitara and crown squamates, even taking into account the confidence intervals both at this route and within for crown squamates, it's still 74 million years. And we don't really have a fossil record for that period. The most unequivocal squamate fossils tend to be from the Tithonian, so very, very latest Jurassic. So what do we think might have been causing this? We're not sure yet. for the PhD, the main hypothesis is that environmental change is driving a lot of these diversification events. But the middle late Jurassic is not, for the terrestrial realm, a particularly interesting period. Continental breakup mostly happened slightly before, mass extinction before. There might be an end Jurassic extinction event, but that would be a bit later. Unfortunately, we can't really test for key innovations because we don't have the fossils for it. But what's increasingly emerging as a potential factor in this is biotic interactions. When you start looking at other groups, you find that there's research to support that sauropod dinosaurs and mammals are also doing well. So potentially there's a larger biotic interaction going on, potentially with competition with mammals or a change in environment that's allowing all of these things to happen. I don't know yet, and I'm not sure at the moment the fossil record is at a place where we can confidently say that it's any of these, but certainly it's pointing towards biotic interactions, and there being quite an interesting pattern in the middle to late Jurassic. So thank you for listening, and I wanted to thank my supervisors, my funding, and everyone who's been helping me. Thank you.